Okay, welcome to Projectile Motion Guide Sheet number 3. This time we'll be looking at what happens when you launch the projectiles at a given angle and how that changes from horizontal launches. Again, key concepts with any projectile is that the only force acting on it is gravity. We're assuming no air resistance. That's a big assumption, but it's one that simplifies our workload at this point. The acceleration value on the Earth would be directed downward and would be 9.8 meters per second. Once projected, its horizontal motion is based on inertia. There are no forces in the x direction, so the object moves with constant velocity in the x direction. Now, as it rises, since gravity is acting downward, the vertical velocity would decrease until it reaches 0. But gravity doesn't shut off, so the object continues to be affected by that gravitational acceleration, and so now it starts to fall. Now that it's moving in the same direction that the acceleration is working, then it gets faster, so its velocity increases in the y direction. Again, as it travels through the air, its horizontal velocity would be constant. Okay, first, again, to reiterate, no matter where you are on the flight, so if we draw the free body, it's supposed to be body diagram. That happened. For a projectile launch at an angle as it rises toward its peak, at its peak or as it falls, it doesn't matter. They're all exactly the same. It is the force of gravity. So it doesn't matter where you are along this parabolic trajectory, the only force acting on the object will be the force of gravity. Now, a common error that people have is to confuse velocity with acceleration. At the top, the vertical velocity would become 0. You would stop for an instant, but the acceleration never becomes 0. The acceleration is always the acceleration due to gravity. Okay, so we have the definition of acceleration. We have s equals u t plus 1/2 at squared. We have v squared equals u squared plus 2as. If we're talking about the x dimension, then the acceleration in the x is equal to delta v in the x over t. Now, that's equal to 0 because there is no change in velocity in the x. Ay is equal to delta vy over t. The place that comes most handy is that that's vy minus uy over t. Therefore, if we want to know, and the acceleration in the y direction is g, if we want to know how fast we're going in the y direction at any point in time, it's going to be g times t, the acceleration due to gravity, times t, plus however fast we started out going, our initial y velocity. Now, that's only the vertical velocity, not the overall velocity. The s, we've already talked about horizontal. If it's the x direction, then it's simply sx. The ux is constant, so it's ux times t. There is no acceleration in the x direction. Okay, so that's our way to measure how far we've traveled. Again, with this equation, if we're looking at v, it's really the velocity doesn't change in the x direction. That particular equation is not much help in the x direction. Now, in the y direction, sy is equal to uy times t plus 1/2 of gt squared. Now, if we had been talking about horizontal launches, then uy was 0. We didn't have to worry about that whole term. Now that term does matter. You should notice that that's a quadratic term, quadratic type equation. Quadratic equations have two solutions. Now, hopefully that makes sense, because on the way up, the ball will be at a height of sy, and then on the way down, it will be at that same height again. So there needs to be two solutions because the projectile will be at the same position twice during a typical launched at an angle flight. We're going to say this other equation for times when it makes sense. It doesn't make sense all that often, but every now and then the distance, it's easier to find it from this than it is from the time equations. Okay, so sticking with those, a projectile is launched with a speed of 31.1 meters per second at an angle of 71.2 degrees above the horizontal. They've already given us the x and y components, so they took 31.1 and multiplied by the cosine of 71.2 degrees to get 10 meters per second in the horizontal, Vx. And then they took 31.1 and multiplied by the sine of 71.2 degrees to get the Vy of 29.4. Okay, now in terms of acceleration, again, in the x direction, there is no acceleration, there's no force. So this is 0 everywhere. And then the acceleration in the y is equal to g, so that's 9.8, and that's down, and that's everywhere, including the top, which again is common error. The velocity in the y direction will become 0, and people often confuse that with the acceleration. Okay, now, since there's no acceleration in the x direction, then the velocity is going to stay constant. It will be 10 meters per second the entire trip. It's the y velocity, the vertical velocity, that's going to change. So as we move upward, then if we're looking for our current velocity in the y direction, it's going to be gt plus uy. In this case, that's going to be negative, or toward the ground, 9.8 meters per second squared, times the time, plus positive, since we're going upward, 29.4. And that's meters per second. So at 1 second, 1 times negative 9.8 plus 29.4 leaves 19.6. Then we'll put in 2 seconds for t, 2 times negative 9.8 plus 29.4, and we'll be down to 9.8 meters per second in the positive direction. We're still moving up, but we're slowing down. At 3 seconds, 3 times negative 9.8 is equal to 29.4, so we will have stopped. Now this is the point where people often say, oh, at the top, then the acceleration is also going to be 0. No, the acceleration in the y stays g. Otherwise, when things reach the peak, and when projectiles reach the peak, they would stay and hover at the peak. And that's not what happens. What goes up must come back down. Now, the reason it must come back down is that at 4 seconds, 4 times negative 9.8 is going to give us a negative value. And when we add that to 29.4, we end up with negative 9.8. Now again, essentially we are saying down is negative and up is positive. So now it's coming down. 1 second later, 5 times negative 9.8 plus 29.4 is going to give us negative 19.6. And then when we reach the 6th second, we'll be at negative 29.4 meters per second. Now, this is another thing that you should notice. Keep in mind that throughout projectiles, symmetry can be your friend. If the launch is up and over and is parabolic, the velocity that you have on the way up will be the same as the velocity that you have on the way down in terms of the magnitude. It's just the direction that is going to change. So uy, your initial velocity of the y, is going to be equal to negative opposite direction velocity at the end. So don't forget symmetry. Symmetry can be very helpful when dealing with projectiles. Okay, that's the end of this first page. We'll move on and look at the others as we go.